Hi, my name's Yoon. I'm making over Physics 2211 Lab 3 black hole. Our objective for this lab was to estimate the mass of a black hole by analyzing the motion of a star orbiting it. With a computational model and ClosScript, we use a personal email address as our NMC to generate a unique star trajectory. We can then analyze the star's motion, its change of momentum, to find the net force on the star at several data points. We then use the net force on the star, the position of the star, and the mass of the star to calculate the mass of the black hole. Our result is that the mass of the black hole is equal to 1.85 times 10 to the 34th kilograms. And here are the corresponding net force values for the system. Moving on, here are some fundamental principles and relevant formulas. We know that momentum p is equal to mass times velocity. The change of momentum over change of time is equal to the sum of its perpendicular and parallel components. We know that F net is equal to dp dt from Newton's second law, the momentum principle. And we know that the force of gravity is equal to g m1 m2 over r squared from the law of universal gravitation. We assume that Fg, for the force of gravity, is the only force acting in the system. As stated before, net force is equal to dp dt, and that is also true for its components. So for example, F net parallel is equal to dp dt parallel, and that is then equal to the change in magnitude of the momentum. The F net perpendicular is equal to dp dt perpendicular, which is equal to the change in direction of the momentum. Now we have some initial conditions for the model code. We're given that the mass of the star is equal to 2 times 10 to the 30th kilograms, and the time interval for each data point is given as 1 Earth day, which is equivalent to 86,400 seconds. Now for the loop code, we can find the initial velocity and the final velocity by splitting up their x and y components. Using those, we can find the initial and final momentum vectors. P initial is equal to mass of the star times v initial. P final is equal to mass of the star times v final. We can then calculate the star's change in velocity and change in momentum. Delta v is equal to v final minus v initial, and delta p is equal to p final minus p initial. Now we can find dp dt. dp dt is equal to delta p over delta t. As stated before, Newton's second law, we know that F net is equal to dp dt. Now we can calculate dp dt parallel. P hat is equal to P initial over magnitude P initial. T magnitude P dt is equal to magnitude P final minus magnitude P initial over delta T. And dp dt parallel is equal to those two components multiplied together. Again, Newton's second law, we know that F net parallel is equal to dp dt parallel. And now we can calculate dp dt perpendicular. dp dt perpendicular is equal to dp dt minus dp dt parallel. And again, Newton's second law, we know that F net perpendicular is equal to dp dt perpendicular. Now we can calculate the mass of a black hole. We set the distance equal to magnitude of star position. We can do this because the star's position is how far away it is from the origin, and the origin is 0. So by rearranging the law of universal gravitation, we can set the mass of the black hole equal to the magnitude of the F net times the distance squared divided by g times mass of the star. The last part of the model code is the arrows. The magenta arrow represents the F net parallel, the orange arrow represents the F net, and the cyan arrow represents the F net perpendicular. As you can see, the F net is always pointing towards the black hole. The F net parallel changes in magnitude depending on if the system is slowing down or speeding up. And the F net perpendicular is always pointing towards the change in direction. And again, here's my results. As for the what does it mean question, what's the difference between net force and the change of momentum? I said they are numerically equivalent, but we can derive the net force from the rate of change of momentum. And net force causes the change of momentum because it changes velocity. In the case of this lab, we solved backwards by finding the change of momentum to calculate the net force. So essentially, they're numerically equivalent, but conceptually different, as they're derived from different things. But what if the black hole was removed and a different black hole was placed in the same location, but the motion of the star remains unchanged and is still only affected by the gravitational force? Could you tell the difference? Would it be possible to find a value for the mass that's different from the old mass? I said if the motion of the observed star remains unchanged, that would mean the net force of the star is the same. That assumes that the mass of the new black hole is the same as the old black hole, so it would not be possible to tell the difference.